Video, what we're going to talk about is solving quadratic equations. And now I'm sure at some point you've heard the term quadratic equation or quadratic formula. And so just to give you a kind of a working definition to start, a quadratic equation, so a quadratic equation is an equation that's equivalent to something of this form: some number times x squared plus some number times x plus some constant, all being equal to 0. And now this might look familiar to our review video because what we end up having here, this is really just a polynomial because we have a term, and a constant in decreasing powers of x. And then remember we talked about degree, so this is degree 2 because our largest exponent of our x is 2. And this is called standard form. Remember, whenever we had a polynomial with everything on one side being equal to 0, we called that a polynomial in standard form. And when we think about solving, because that's going to be our biggest point here, remember solutions, those are the values that make our equation true. And so to go back and kind of point out some of these keywords. So this is called a quadratic equation. It's a little dark. And we have solutions are values that make our equation true. So solutions make our equation true. So what we're going to be looking for here are values that make our quadratic equations true. And that's what we'll call solving quadratic equations. Now I'm going to reintroduce something, and you may not have heard it called this before, but we used it when we were factoring in our review sections. This is called the zero product principle. Fancy name for something that I think you'll find is rather intuitive. So let A and B be two algebraic expressions. So remember, expressions are a collection of terms, but there's no equal sign. So there's constants, variables, and then our operations of addition, subtraction, multiplication, division, and square root. If A times B is equal to 0, so if we take two things and multiply them together and we get 0, then we know A equals 0, B equals 0, or both equal 0. And now let's think about that. If I have 2 times x equals 0, following our parallel of our letters from above, and let me get another color, if we call this here A and this here B, to make this true, we know that x has to equal 0. And so our zero product principle says that if A times B equals 0, so we have something times something equals 0, then either the first term is 0, well, 2 doesn't equal 0, or B equals 0. And that's what happens to be the case here. So we use this whenever we're solving quadratic equations because we're always going to work in the standard form of some polynomial is equal to 0. And then what we end up needing is that since we'll end up creating a product on one side, we're going to want to show that one or both are 0. So let's go through. And once I do some factoring examples, you're going to be like, this is exactly what we did when we were solving by factoring in our first week. But what we're going to look at, so we have some solution strategies. I'm going to look at them each in turn. So we have our first solution strategy, which is factoring. Our second solution strategy is called the square root method. Our third is called completing the square. And our fourth is the quadratic equation. Not the quadratic equation, we're talking about quadratic equations. The quadratic formula. And so we're going to look at these four solution strategies for solving quadratic equations. So now we'll go ahead and move on to the first, factoring. So when we look at factoring, we'll have something that looks like this. 2x squared minus 9x plus 4 is equal to 0. And remember, we had a process that we talked about in a previous video, that when we factor, we find factors of c, our constant term, that sum to b, our middle term. And remember, whenever our coefficient of our leading term, our leading coefficient, whenever this wasn't 1, if it's not 1, we have a little half step. So I think this was 2.5. What we end up having is we need to calculate our product of a and one factor, right? Because when we would distribute it back out, we end up having this instance where the 2 is going to be multiplied by one of those factors. And so for 4, we have two factor pairs. We have 1 times 4 and 2 times 2. And so one of those needs to be multiplied by 2. So we're either going to have 2 plus 4 or 1 plus 8. And here, because they're both the same, it doesn't matter. We're going to have 2 plus 4 or 4 plus 2. Well, that's only 6. That's 9. That's 6. And that's still 6. And then we go back and look at our original, and it turns out that this 9 is what we want. And so to factor it, what we end up doing, we have our 2x and an x here, because when we distribute those will give us a 2x squared. And then what we need is a 9. So we know that one of these is going to be a 1, and the other is going to be a 4. And we know that this 2 needs to be multiplied by the 4. So it goes over here, 1 and 4. And then we look at our signs. They need to sum to negative and multiply to be positive, so they'll both be negative. And now let's go ahead and just check that along the side, because it's always important that we do that. So here we have 2x minus 1 times x minus 4 times 2x minus 1. Distribute that through 2x squared minus x minus 8x plus 4. 2x squared minus 9x plus 4. Whew, that's what we started with, which means we're on the right track. And now this is where the zero product principle comes in. Zero product principle. We have one expression and another that equal 0 in product. So the zero product principle tells us that for this to be true, we either need the a equals 0 or b equals 0, or they could both end up being 0. So if a was equal to 0, what we have is 2x minus 1 equal to 0. And if b equals 0, we have x minus 4 equal to 0. And so now we can solve each of these on their own. First thing we'll do, one of our equivalence processes, is we can add the same to both sides. 2x equals 1, which means x is equal to 1/2. When we divide by 2, add 4 to both sides. X equals 4. Let me go ahead and go back. I'll write in this divides by 2, just so we see what happened there. So this is true. 2x minus 1 times x minus 4, which is equivalent to 2x squared minus 9x plus 4, is equal to 0 whenever x equals 1/2. So our solutions are x equals 1/2 and x equals 4. And if you want, you could say x is equal to, and then you can write a set, 1/2 and 4. I mean, I guess more precisely, we should use this fancy e symbol, but I won't hold that against you. So if x is equal to 1/2 or 4, we should get 0. And now we know, since this factor multiplied back out to the original, and 1/2 made this one 0, and 4 made this one 0, when we plug them in here, they should give us 0. And so we'll check just on this one, but generally speaking, we won't have to go back and check in the original. So if I have 1/2, I have 2 times 1/2 squared minus 9 times 1/2. I got a little excited. So we have 2 half squared is 1/4, so 2/4 minus 9/2 plus 4. So let's get a common denominator of 4. So we have 2 over 4 minus 18 over 4 plus 16 over 4. Well, 2 minus 18 is negative 16, plus 16 is 0. So that one definitely worked. And then we'll check 4. We have, and I won't write the work for this, we have 2 times 16, which is 32. 9 times 4 is 36, so it's 36, or 32, minus 36 is negative 4, plus 4 is equal to 0. And so that one is also correct. So once we have that, we know we're good to go, and we have our solution. So generally, right, our process is find our factors that sum to b, factor it, and then use the zero product principle. And so we'll go ahead, and what we can do is try another example with factoring, and that'll be enough, I think, examples of factoring here. We have x equals x squared minus 12. So something that's important to remember is we need this in standard form. So we write in standard form. And so we need our x squared minus x minus 12 equal to 0. I move this to this side by subtracting an x from both sides. And then we find our factors of c that sum to b. And since our leading coefficient is 1, we don't have to worry about any of our products. So we have 12 is either 12 times 1 or 4 times 3. And it's not just 12, but it's a negative 12. And so we really have negative 12 times 1 or negative 1 times 12. Negative 4 times 3 or 4 times negative 3. And we need to know which of those sum to negative 1. Well, that sum is negative 11. This is positive 11, negative 1. Well, that's what we want. So we have a negative 4 and a 3. So we bring this down. And we have now x and x equals to 0. And we said our terms were, or our factors were negative 4 and positive 3, negative 4, positive 3. And that was step 3, factor. and I'll put 3a, check. So if we distribute this through, we have x minus 4 times x plus 3 times x minus 4, x squared minus 4x plus 3x minus 12, x squared minus x minus 12, which does look like our original, so we're good. And then we use our zero product principle, so we know that either x minus 4, if I could write x minus 4 is equal to 0, or x plus 3 is equal to 0. And now we can solve each of those separately. Add a 4 to both sides, subtract a 3 from both sides. We have x equals 4 or x equals negative 3, because we know one or both are 0. And then you can, so there's check your factoring, and then check solutions. And I would say whenever, notice, right, that we had to rewrite this in this form. When you're checking your solutions, I would say check them in your original, because that'll help you know if you maybe made a mistake when you rewrote it. So we had x equals x squared minus 12. So let's try x equals 4. Does 4 equal 4 squared minus 12? Well, that's a question. With 4 equals 16 minus 12. 16 minus 12, 4 does equal 4. So we know that solution is good. And then similarly, x equals x squared minus 12. Check our negative 3. Does negative 3 equal negative 3 squared minus 12? Well, is it true that negative 3 is equal to 9 minus 12? Well, negative 3 does equal negative 3. So our solution is correct. And then I would say just good practice is rewrite solution. So our solutions are x equals 4 and x equals negative 3. And so that, right, is not too bad. It's pretty similar to when we were factoring, but we also know that there are only certain instances when you can factor. And so it's important that we look at, well, what happens when we can't factor? So that's gonna lead us to an example where we look at the square root method. So this is our second process, the square root method. Square root method. And this is going to be worthwhile because what we end up seeing is that in this first example, 2x squared equals 50. If we want to write this in standard form, so we have 2x squared minus 50 is equal to 0, we don't have an x term. But it turns out we can factor this. Because first, let's go ahead and divide everything by 2. And we'll have x squared minus 25 equals 0. And you wouldn't have to divide by 2, and I'll show you what it would look like if you didn't. And this was our special. We had a special instance where we had something squared minus another perfect square. And that we called the difference of squares. And so this factors into x minus 5, x plus 5. And that's a formula. X plus 5 is equal to 0. And so our zero product principle says that x minus 5 equals 0, x plus 5 is equal to 0, or x equals 5, and x equals negative 5. Now just to show you how you would do this without dividing by 2, you'd have a 2x and an x. We need two factors of negative 50 that when one of them is multiplied by 2, they sum to 0. Well, that turns out that that's 10 and 5, and it doesn't matter which one has our negative. So we have minus 10 plus 5. We can double check that by distributing 2x squared plus 10x minus 10x minus 50. Those cancel, so we got back where we started. And if we use our zero product principle here, 2x minus 10 equals 0, or x plus 5 equals 0, 2x equals 10, or x equals 5 by dividing both sides by 5. Or here, subtract 5 from both sides, negative 5. Right, so see, we get the same solutions whether or not you divide by 2. I would say, generally speaking, it's easier, if you can, to work with a leading coefficient of 1, as long as it's not going to give you fractions. Like, if that weren't 50 and it were like 49, like, definitely wouldn't recommend dividing by 2 first. I mean, it wouldn't have worked out in that case if it were like 98. But even then, you wouldn't have gotten a fraction. So, get leading coefficient equal to 1 unless it'll introduce fractions when you're using the square root method. But this was just factoring, right? So that was all factoring. And you're like, you said that we were going to talk about the square root method, but you just showed us another factoring example. Well, let's say we started this way instead. We have 2x squared equals 50. Go ahead and divide both sides by 2. X squared equals 25. And one of our equivalence rules we have is we can take the square root of both sides. So here we have the square root of x squared gives us x. And then the square root of 25, well, 5 times 5 is 25. But negative 5 times negative 5 is also 25. So it's important that we always introduce a plus or minus when we take the square root of both sides. And that's because 5 times itself is 25, but negative 5 times itself is also 25. And so whenever we do the square root of both sides, we introduce a plus or minus. And so let's look at another example. And I'm going to go to another piece of paper just because I don't want to run out of space. Here we have another example. 2x minus 3 squared equals 25. And I say use the square root method. Well, we can take the square root of this because it's a square, and we already talked about the fact that 25 is a square. So the square root of this is 2x minus 3, and the square root of this is plus or minus 5. Now you might be wondering, well, what happens if I put the plus or minus on the other side? 2x minus 3 equals 5. And we're like, well, that's where our plus or minus is going to be. Well, we'll look at both of those in turn. I'm going to work on this side first. So we have two cases. 2x minus 3 equals 5, or 2x minus 3 equals negative 5. And we'll solve each of those in turn. We have 2x equals 8, x equals 4. Or we have 2x equals, add a 3 to both sides, negative 2, x equals negative 1. And we always need to check our solutions in the original. So we have 2x minus 3 squared equals 25. Well, let's find out. We either have 2 times 4 minus 3 squared might be 25. Or we have 2 times negative 1 minus 3 equals 25. Well, 2 times 4 is 8, minus 3 is 5, so 5 squared does equal 25, so we're good with that one. And over here we have negative 2 minus 3 is negative 5 squared does equal 25. So that solution is good. So here we have solutions. Our x equals -1, x equals 4. Now I said, what happens if we put our plus or minus on the other side? Well, here we have a 2x minus 3 equals 5 in the plus case, or we have a negative 2x minus 3 equals 5 in the other. And so once we're looking at that, we can solve each of them independently like we had in the past. 2x minus 3 equals 5, so 2x equals 8, or x equals 4. And over here, let's go ahead and distribute this negative through. Negative 2x plus 3 equals 5. Negative 2x equals 2. X equals negative 1. Well, and look at that. X equals 4. X equals 4. X equals negative 1. X equals negative 1. So it doesn't matter where you put the plus or minus. I would say it's often easier to just stick it on your constant term that's by itself. Otherwise, you're going to have to remember to distribute that negative through. But it doesn't matter to me which way you proceed, as long as you remember to introduce the plus or minus. And so that's our square root method. Usually you're going to do that when you have something squared equal to something squared. Otherwise, it's not really going to simplify things. It's going to actually make it more complicated if it introduces a square root. And so that would generally be my recommendation. Sometimes it's unavoidable, and sometimes it is easier to work with a square root, but I would say generally speaking, you're going to want to use that particularly whenever it simplifies what's happening. Now our third solution strategy is completing the square. And so let's look at an example. Y squared plus 10y to 0. Now we could factor this immediately, right? We can pull a y out, y plus 10 equals to 0. And that's going to tell us that either y equals 0 or y equals negative 10. Or, and this is an instance where it's like, well, why wouldn't I just solve it that way? We're going to look at ones that are a little bit more complicated, and you'll see why we're going to want to look at completing the square, but I wanted to pick this one because I think it's a little bit easier to see. So let's say that this length is y. So we have y squared. So we have a y and a y. And then 10y, well, we can think about putting, if this is 1 unit wide, and this is still y, right? This whole rectangle is y. So I'm going to add 5 of them over here. One, two, three, 4, 5. I'm going to add 5 of them down here. 1, 2, 3, 4, 5. So we have y, and here, so this whole thing is y squared. And here we have 5, and here we have 5. Remember, our widths here are y. So this whole piece, and this is going to look a little messy, but I'm going to do it anyhow. This whole piece is 5y. This whole piece is 5y. So if we look at that sum, we have y squared plus 5y plus 5y, which is our y squared plus 10y. Right? That's where we started. That's where that's all accounted for. My question is, how many 1 by 1 squares do you need to complete the square? So that is down here in this corner, how many 1 by 1 squares do you need to complete this large square that is y plus 5 times y plus 5, right? Y plus 5, y plus 5. Well, if we just extend our lines down and extend our lines over, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. We need 25 squares to complete the square. And we also could have gotten that because we knew that this was 5, and that was 5, and 5 times 5 is 25. So let me bring this together. Suppose you didn't want to solve it by factoring just a y out, but instead you wanted to write it as a sum of squares. So I'm going to rewrite my original. Y squared plus 10y equals 0. And I'm going to leave a blank. So my question was, how many 1 by 1 squares do you need to complete the square? And we said 25. So my equivalence properties, I can add 25 here as long as I add 25 here, right? So I have y squared plus 10y plus 25 equals 0 plus 25. But now, I just convinced myself that y plus 5 times y plus 5 equals y squared plus 10y plus 25, because we had a y squared, a 5y, a 5y, and a 25. So this I can factor as y plus 5 squared equals 25. And so you're like, okay, that looks a little bit easier. And then what can we do? We can use our square root method. We can take our square root of both sides. Y plus 5 equals plus or minus 5. And so I'm going to write this a little differently in a way I haven't seen it. Y equals, I can subtract this 5 over, negative 5 plus or minus 5. And so if I have negative 5 plus 5, what we end up getting is 0. Or we get y equals negative 5 minus 5, negative 10. And now note, that's exactly what those two solutions were. Y equals 0, y equals negative 10 by the 0 product principle. And so far you're like, okay, you did that, but why would I ever want to do that? Especially because of that form, I could solve it directly from the beginning. Well, here I will show you an example of when you would want to do this. If I have, for example, we have x squared plus 6x plus 7 equal to 0. We can look at our factors of 7. Well, it has to be 1 times 7. And what factors of 7 when some give us 6? Well, the answer is none. Because 1 plus 7 is equal to 8. This doesn't factor. And remember, we called those irreducible. So whenever we complete the square, my first step is going to be move the constant term. I want you to have it of the form x squared plus 6x. I'm going to always leave a space equals negative 7. So I subtracted 7 from both sides. And then add your blank. So add a blank and add a blank. Because we need to remember to add it to both sides, or we're not going to preserve equivalence. And now we need to know how many little squares do we need to complete the square. So let me go ahead and draw my array. Here I have x squared. And remember when I had 10, I put 5 and 5? Well, now that I have 6, I'm going to put 3x here and 3x here. Which means we have something that looks like that. And so how many squares are there here? There are 9 squares. And you're like, well, how did you know to draw that many? Well, we know that this is x plus 3 and x plus 3. X plus 3 squared equals x plus 3 times x plus 3, which is x squared plus 3x plus 3x plus 9. And that's where those 9s come from. And so my blank, so after 3 you'll complete the square. And I want us to think about this as a literal square. I think you should always draw that square. We have 6x, so we had x squared plus 6x plus 9. So our blank is 9. Complete the square. Fill in the blank. Add 9 to both sides. And let me go ahead and move this down here. So we have x squared plus 6x plus 9 equals negative 7 plus 9 is 2. For step 5, factor. We have x plus 3 times x plus 3, right? We said that right here, equals 2. Or let's go ahead and write that as a square. X plus 3 squared equals 2. We can use our square root method. Take our square root of both sides. X plus 3 equals plus or minus the square root of 2. And I'm just going to write it as the square root of 2 because if you put that into your calculator, you're going to get a decimal and you're going to get an irrational decimal, which means that it never terminates or repeats. And instead of introducing some sort of rounding error, we're just going to leave it as the square root of 2. And then we can subtract a 3 from both sides. X equals negative 3 plus or minus the square root of 2, which means that our two solutions are x equals negative 3 plus the square root of 2 and x equals negative 3 minus the square root of 2. So solutions. We go there. Now notice I didn't just start, once I had x plus 3 squared, I didn't just say, I'm going to use red as soon as I find that pen. So this is not what we'll say. From here, this does not mean x plus 3 equals 2, right? Our zero product principle only works when this right side is 0. So we do not get to say that. Instead, we have to follow our square root method, and then we can get our solutions. and we can always go back and double check. And so if we would take -3 plus the square root of 2, I think that's worthwhile. I'm going to copy this over. So we have our original x squared plus 6x plus 7 equals 0. And our solutions were -3 plus the square root of 2 and -3 minus the square root of 2. And it's good practice to check. So if we have x squared plus 6x plus 7 equals to 0, let's check -3 plus the square root of 2 squared plus 6 times -3 plus the square root of 2 plus 7. Does that equal 0? Well, if we distribute this out, -3 plus root 2, -3 plus root 2, we're going to get a 9 minus 3 root 2 minus 3 root 2 plus 2, and then plus 6 times -3 is -18, plus 6 root 2's, plus 7. What does that equal? 0. Let's go ahead and get all of our constants together. So we have 9 plus 2 is 11, minus 18 is -7, plus 7 equals 0. And then here we have -3 root 2's and -3 more, so that's -6 root 2's plus 6 root 2's plus 0 equals 0. Check. And I'll leave the other one for you to check, but it should work out. And if not, you might want to send me an email. And let's go ahead and do one more example. So I'll go to another new page. And what we have here is x squared minus 3x equals 0. So solve that by completing the square. Before we do, I want to look back at our two previous. No, not that page. We want this page and this page. If we had a 10 here, we ended up wanting 25 here. And when we had 6 here, we ended up wanting 9 here. So what's the pattern there? Well, when we drew our square, instead of that 10, we ended up putting a 5 here and a 5 here. So we split that middle term into 2 pieces, and it turned out when you squared those, we got 25. And the same happened here. We put half of our 6 here, half of our 6 here, and when you squared that, you get 9. So our pattern is, this is important to remember, our pattern is you add b divided by 2 squared to both sides. And you're like, well, why didn't I just give you a rule at the beginning? Well, I wanted you to see where the rule came from. In our practice of drawing our squares, and we put that same bit, and so I have a colored copy here, I ended up adding a 5y here and a 5y here, and you're like, well, why didn't you just put all 10 up there? Right? It's called completing the square. We needed the length of this side and the length of this side to be equal. And so if I didn't add 5y here and 5y here, I would have a rectangle. So we will always need to add half the middle term squared to both sides. So if I wanted to put all of my steps back together, step 1 is move the constant term if you need to. Here there's no constant term. 2, we add our blank. So here we have x squared minus 3x plus something equals 0 plus something. We complete the square. Which we now know means add b divided by 2 squared to both sides. Which is complete the square, which is filling in the blank. Fill in the blank. And then we factor. We use our square root method. We rewrite our solutions. And we check. So let's work through that process with this example. So we added our blank, we complete the square, and so to complete the square, we have to add the b divided by 2 to both sides. So we have negative 3, so b equals negative 3. This is kind of scratch work on the side. So negative 3 divided by 2 squared is 9/4. So we're going to add a 9/4 to both sides. And now we can factor. It's going to be our x minus, and whenever you factor, it's not just 9/4, but it's the square root of 9/4 squared is 9/4. And in this case, which is always the case when we factor a square, 9/4 is a perfect square, so x minus 3/2 squared is 9/4. And then we use our square root method. X minus 3/2 equals, and we remember taking a square root introduces a plus or minus. Plus or minus 9/4 divided by, or the square root of that is plus or minus 3/2. And so when we move this down, we have two possibilities, x minus 3/2, before I go that far, we need to get them on one side. X equals 3/2 plus or minus 3/2, which means that x equals either 3/2 plus 3/2, or x equals 3/2 minus 3/2. Well, here we have 6/2, or 3, and here we have x equals 0. And so there are often ways that we can double check. If we had factored this directly, x minus 3, x equals 0, or x equals positive 3. And you're like, okay, so I see why we could do that. Still could have just factored that out to begin with. That would often be the case. But I'll give you a general reason why it is that we might want to be able to complete the square. And that's going to be our last strategy. And that's called the quadratic formula. So suppose we have some general ax squared plus bx plus c is equal to 0. Now there's something I didn't tell you about completing the square, but there was something that was always true. This leading coefficient has to be 1. So leading coefficient must be 1. Leading coefficient must be 1. I'm going to write it here for good measure. Leading coefficient must be 1. But that's not generally the case. Generally speaking, we have some a term. And so to get that as a 1, we can divide every term by a. So what we end up with is x squared plus b over ax plus c over a is equal to 0. And then our first step of completing the square is to move the constant term. So we have x squared plus b over ax equals negative c over a. And then we always add our blank. Add our blank. And then our process was add middle term divided by 2. So b over 2a squared to both sides. So b over 2a squared, b over 2a squared to both sides. And what that means then is this side we can factor as x plus b over 2a squared equals, and I'm actually going to distribute that exponent. So we have b squared over 4a squared minus c over a. And I'm going to work on simplifying this side, but I'll just rewrite this for the ride. X plus b over 2a squared equals, our common denominator, we have a 4a squared and just an a. So we multiply top and bottom by 4a. And since that's 1, it doesn't change our value. We have b squared over 4a squared. And multiply that minus 4ac over 4a squared. Right, and I'm doing this because I want to use the square root method. X plus b over 2a squared equals, we have a common denominator, b squared minus 4ac all over 4a squared. Use our square root method. We have x plus b over 2a equals, I'm going to leave that square root, b squared minus 4ac, but I can take the square root of that denominator and get 2a. We want to get our x alone, so x equals negative b over 2a. But what did I forget to introduce? A plus or minus. So we have negative b plus or minus the square root of b squared minus 4ac all over 2a. And that's a common denominator, so let's just throw them together. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And now some lights might be flashing in some of your heads, because this x equals negative b plus or minus the square root of b squared minus 4ac all over 2a is called the quadratic formula. For any quadratic, ax squared plus bx plus c equals 0, its solutions are x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So that means always, 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 if you have a quadratic, its solutions, the values that make it true, are given by negative b plus or minus the square root of b squared minus 4ac all over 2a. So let's look at some of our examples we've done already. So here we had y squared plus 10y. I'm trying to decide where I'm going to put that. Y squared plus 10y plus 0. So a equals 1, b equals 10, and c equals 0. The quadratic formula tells us that x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And if we substitute each of those, x equals negative 10 plus or minus the square root of 100 minus 4 times 1 times 0 all over 2 times a. And so that equals negative 10 plus or minus the square root of 100 minus 0 over 2. So that gives us negative 10 plus or minus 10 over 2. Negative 10 plus 10 over 2. Negative 10 minus 10 over 2. We have 0 over 2, which is 0. Or negative 20 over 2, which is negative 10. And if we look back, y equals 0, or y equals negative 10. We could also look at another example. We had our very first example of the day was 2x squared minus 9x plus 4 equals 0. So a equals 2, b equals negative 9, and c equals 4. Our quadratic formula tells us that x equals negative b plus or minus the square root of b squared minus 4ac all over 2a, which is negative 9 plus or minus the square root of negative 9 squared minus 4 times a times c all over 2a. So that is 9 plus or minus the square root of 81 minus 4 times 2 is 8 times 4 is 8, 16, 32 over 4 equals 9 plus or minus. So 81 minus 32, 81 minus 30 is 51 minus 2 more is 49, plus or minus the square root of 49 all over 4. So that's 9 plus or minus 7 over 4. 9 plus 7 over 4, 9 minus 7 over 4. 9 and 7 is 16. Move that up a little bit. 9 and 7 is 16 divided by 4 is 4. 9 minus 7 is 2 over 4 is a half. So we have 9 and a half are our two solutions. And no, that's not 9. I can't read. It's a 4. It's 4 and a half. 4 and 1/2. So, the takeaway there is, no matter what your quadratic equation looks like, the quadratic formula will always give you your two solutions. Sometimes this calculation is a lot more work than just factoring and solving directly. Sometimes it's easier to factor and solve, to use the square root method and solve, and sometimes you would rather complete the square. So, but sometimes those are less work, but this will always work. This will always give you solutions to any quadratic equation. And so, just a couple points of emphasis. So some points to emphasize, and then we'll be done. Points to emphasize. So I'll just use bullets. To complete the square, leading coefficient must be 1. Our pattern for completing the square, is add b over 2 squared to both sides. Our quadratic equation, quadratic formula always works. Especially when you can't factor. And square root always introduces a plus or minus. And those are our 4 strategies for solving quadratic equations. I'll see you in the next video, everyone.